Hello friends, welcome to my channel. Let's have a look at problem 323, number of connected components in an undirected graph. In a previous video, we shared a solution using disjoint set data structure, also as unified. And in this video, we're going to share a solution based on traversal algorithms. This problem asks us to return the number of connected components in an undirected graph. So here are two examples. In example 1, so there are 5 nodes, and this is the edge list. So the return is 2 because there are 2 connected components. And in example 2, the return is 1. As we can see, this graph itself is singly connected. So the constraints about this problem are listed here. So there are several points we want to go over. So first is the number of nodes is bounded above by 2000, and the number of edges is bounded above by 5000. And also there are no self-cycles because AI does not equal to BI. And also there are no repeated edges. So that's the constraints on this problem. So now let's look at the method. The method we are going to present here is traversal method. So here you can use Bfs or DFS. So the difference lies in the container we choose to iterate in the while loop if we want to use iterative fashion. So here let me specify the containers. So for breadth first search, the container is queue, and for depth first search, the container is stack. So in this problem here, or in this video, we're going to share a breadth first solution and in iterative way. So we feel the iterative way helps understand the problem a little bit better. So with that said, let's look at the code. I'm going to split the code into 3 parts. First is build the graph, and after that we are going to write a breadth first search helper function to find the connected components. Thirdly, we count the number of connected components. And prepare the return. So let's first look at step 1, build the graph. I'm going to use the adjacency list to represent the graph. For this, let me first initialize a container. So I'm going to use collections.defaultdict directory, and the container will be a set. The set will store the neighbors of the corresponding key. So let's walk through the edges for UV in edges. Then I'm going to add V to the neighbors of U, and also I'm going to add U to the neighbors of V. So this way we finished building the graph. So now let's look at the main work, that is the Bfs Helper Function for locating the connected component. So here let's define Bfs. It accepts in argument it's a node value, let's say 0, 1 or n-1 in this problem. So here we are going to use a set to represent the connected components, in other words the nodes contained in that component. So I'm going to initialize a set called visited, and also for the traversal we are going to initialize a container. Here I'm going to use it as a queue. So starting from the input argument I. Then I'm going to do the iteration. So while queue is not empty, so we're going to use the queue behavior. So queue pop from the left. So I'm going to use the left as the head of the queue and use the right as the tail of the queue. And then we are going to check if node not in visited. Then we are going to add this node to the visited site. Add the node corresponding to add this node to this current component. And then we are going to look at the neighbors. For neighbors in graph node, then we are going to check if neighbor not in visited. Then we are going to include this neighbor. So q append this neighbor. So after this while loop, we get all the nodes in this connected component starting from I. Then we are going to return visited. So this way of using a set of nodes to represent a connected component help us to avoid repetition in step 3. For step 3, first let me initialize a result that is 0 initially. Represents the number is 0. So then we are going to count the connected components. For that, let me first initialize a visited site to monitor the nodes we have already visited to avoid repetition. Then we are going to look at all the nodes, and we want to do breadth first search from the nodes. Then we first need to check if I not in visited. So if it's already visited, we just continue. Otherwise, we are going to do breadth first search starting from this I. And then after we do the breadth first search, we are going to get one new connected component. So we increment the result by 1. And at the same time, we're going to update this result by a unit operation. So to add the new visited nodes. So that's it for the main logic. Then we are going to return the result. So that's the full code for this problem. So let's do a special case check. Yeah, it passes a special case. Now let's look at a generic case. So run on step. So here, I guess we should add u. So we are building, we make a tuple. So now let's submit again. Yeah, it passes the generic case. So I guess for this video, so the structure is what we want to convey. So first we build the graph, and then we write a breadth first search function to locating the connected component, and the third step basically is a counting procedure. So before we end this video, so here if we choose to use q pop from the tail, then actually we are using a stack behavior. So the corresponding function is actually depth first search. So this is one point. Another point is that here we checked membership for node in visited, not in visited, and here for neighbor, not in visited. Actually, this code can be shrinked one line by one line. So that's another thing. And thirdly, actually, it's good to compare this format of solution to this problem with the format of unified solution to this problem. So it's good to compare the similarities and dissimilarities. That way we have a better feeling about this kind of problems. That's about it. Thank you very much.